Hey, I'm Dr. Scott Coste, back with another demo. Today what we're going to talk about this time is some inorganic chemistry. And so what we're going to show you today are the colors of inorganic ions dissolved in water. The color of a ion in solution depends on the energy separation of the d orbitals, and the intensity comes from the loudness of the transition. And so to demonstrate the loudness of the transition, what I'm showing here is a variety of test tubes in which I'll dissolve salts going from D0 up to D10. So first what I'm going to show you is nickel sulfate. There you go. You can see this beautiful aquamarine color forming. And so what we're showing here, what this has is now a spin-allowed transition, which enables us to see a much more apparent color in solution. And if we compare this now to copper, which is a D9, so it's going to have a spin-allowed transition, but it's going to have a different energy because it's a different energy separation of the d orbitals. You can see that it results in a pretty blue color now. But if we move to zinc, which is D10, so its d orbitals are filled, we should see absolutely no d to d transition. Therefore, it should be essentially colorless, which we do see here. So now, if we actually go back over here to manganese sulfate, which is a nice pink powder, we dissolve the manganese sulfate in solution, you can see that it's pretty much colorless. And so that stems from the fact that manganese sulfate is high spin D5, so all 5 d orbitals are equally occupied by 1 electron, so the lowest energy transition is spin not allowed, which therefore means it has a very low extinction coefficient and essentially colorless. So I'm going to show you potassium permanganate. That is a D0. You would think that with no d electrons, you would essentially have no color, but instead what we see is this vibrant purple color. And that is because this is not from a d to d transition, which is what governs the transitions of these compounds. Instead, potassium permanganate has a transition that arises from the oxygens. Now we can have a little extra fun, and we could take the copper sulfate solution, which is a hydrated copper ion when dissolved in water, and we can add in a little bit of ammonium hydroxide here. So if we drop the base, you can see a beautiful color change. As we add in the ammonium hydroxide solution, the amine coordinates to the copper center and forms a lower symmetry complex. And that lower symmetry complex relaxes the selection rules, allowing for a more intense blue color to form. Here we have an array of compounds from the first row in the D block showing an array of colors due to the different occupancies and loudness of the transitions of the d orbitals.
That was amazing!